Hi. So today I will be discussing SCR. SCR is a four-layer semiconductor device of alternating PN material. The word thyristor is coined by the thyratron and transistor. Two states. It has on and off. So SCR meaning it is a silicon controlled rectifier. Trade name of thyristor is commercialized by General Electric in 1957. Four-layered three-terminal device have the highest power handling capability, rating of 1200 volts or 1500 ampere, switching frequency 1 kHz to 20 kHz. Four states, we have reverse blocking mode, we have reverse conducting mode, we have forward conducting mode, and we have forward blocking mode. So this is the symbol. We have anode, we have gate, and we have cathode. What is the symbol inside? So that is an alternating PN, but the gate is on the P, the second P here, the anode and the cathode. The internal is that it is connected in PN, and the last P, it has a gate. So meaning it is a connection of a PNP transistor and an NPN transistor where it has an extra gate as a terminal. Three important thyristor specifications. So we have forward breakover voltage or the VBR or breakdown voltage. This is the voltage at which the SCR enters at the forward conducting region. We have a holding current. This is the value of the anode current below which the SCR switches from the forward conduction region to the forward blocking region. And we have a gate triggered current or IGT. This is the value of the current necessary to switch the SCR from a forward blocking region to the forward conduction region under a specified condition. They have difference in the specification graph. As you can remember, the dia, it has symmetric here. When you reach the breakover voltage, it will conduct. If you reach the reverse breakover voltage, it will conduct in the same pattern as the positive one. Here it has, when you reach the negative breakover voltage, it will be in the reverse avalanche region. It will be in the reverse blocking region. Characteristic of thyristors: when the anode is at a positive potential with respect to the cathode, with no voltage applied at the gate, junction 1 and junction 3 are forward bias, while the J2 is in the reverse bias. As J2 is reverse bias, there will be no conduction. Now, if the forward potential or the VAK, anode to cathode, is increased beyond the breakdown voltage, VBO, of the thyristor, avalanche breakdown of J2 takes place when the thyristor starts conduct. As you can remember from the Shockley diode, the operations of all the thyristors are the same. We have to break down the J2, the junction 2, for it to operate. Here in the thyristor, if the J2 breaks down, the thyristor starts to conduct. If a positive potential VG or the gate voltage is applied at the gate terminal with respect to the cathode, the breakdown of the junction 2 occurs at a lower value of VAK. By selecting an appropriate VG, the thyristor can switch into a sudden conduction. So the difference of the SCR to the Shockley, you can trigger the Shockley through the gate, not just only from reaching the breakover voltage, but by applying the VG in the gate terminal, making it VG more positive than the cathode, it will trigger the SCR to conduct. That's why we have a triggering device. As you can see here, the difference from the earlier curve is that you have a forward leakage current where this broken line represents gate triggered or the VG that switches the SCR into a sudden. We have types of thyristors. We have a unidirectional thyristors. The thyristors which conduct in forward direction only are known as a unidirectional thyristor. So we have SCR as unidirectional thyristor. SCR, this one. Characteristic: blocking when reverse bias, no matter if there is a gate current or not. conducting only when forward biased and there is a triggering current applied at the gate. Once triggered on, will be latched on the conducting even when the gate current is off. Turning off, decrease the current to a near zero, which the effect of the external power circuit. If the anode to cathode voltage is further increased to a large value, the reverse bias junction will break down due to the avalanche effect, resulting in a large current through the device. The voltage at which the phenomenon occurs is called the forward breakdown voltage. So we have two important current terms. So we have the latching current. After the SCR has switched on, there is a maximum current required to sustain the conduction even if the gate supply is removed. This current is called the latching current, associated with turn on and is usually greater than the holding current. While the holding current, after an SCR has been switched to the on state, a certain minimum value of anode current is required to maintain the thyristor in the on state. If the anode current is reduced below the critical holding current value, the thyristor cannot maintain the current through it and it turns off. So the difference of the two is that when you reach latching current, it will continuously supply current and it will continuously in the conduction state. While if that is a holding current, during the on state, it gradually lowers the current below the holding current value. The thyristor cannot maintain the current through it and turn off. So this is the effect of the gate voltage. It depends on how much the voltage of the gate for it to have the triggering effect. 4 modes of operation of a thyristor. So we have reverse blocking mode, the thyristor is open circuit. Reverse conducting mode, thyristor is closed. Forward blocking mode, the thyristor is open. In the forward conducting mode, the thyristor is closed. So reverse mode. Reverse blocking mode where the anode to cathode is negative. When a negative voltage is applied to the anode with respect to cathode of junction 1 and junction 3 are reverse bias. We know that if that is reverse bias, the junction 2 is forward bias and that is in open switch, non-conducting state. The SCR is in its reverse blocking state. If that is reverse conducting state, if you apply a negative voltage, that will make the J1 and J3 more positive, then that will be making the SCR close, which reverses the direction. A large current gives more losses in SCR, dissipating in the form of heat, thereby damaging the SCR. So at least here you can know that SCR cannot operate in the reverse mode. That's why the graph is different compared to the diagram. So we have a forward blocking mode. When the positive voltage is applied to the anode with respect to cathode, the junction 1 and junction 3 are forward bias. Junction 2 is the reverse bias. The SCR is in the forward blocking state and the gate signal is not applied. A depletion layer is formed in the junction 2, so no current flows from the anode to cathode. If no current in the anode to cathode, that means it is open. Forward conducting state, when the positive voltage is applied on the gate terminal, making J1 and J3 more positive than and breaking down the J2. So that means that is in the conduction. So the SCR acts as a closed switch and conducts a large value of current with a small voltage drop. With the applied of this SCR gate signal, the SCR state changes from a forward blocking state to the forward conducting state. Once you apply voltage at the gate terminal, it produces a forward current that will make the SCR in the latching state. Without the gate signal, SCR changes from a forward blocking state to forward conducting state, the forward breakdown voltage. When the gate signal value is increased, the latching happens from low VAK voltage as mentioned in the figure. In the presence of forward current, after the thyristor is turned on to a suitable gate voltage, it will not turn off even after the voltage has been removed. The thyristor will only turn off when the forward current drops below the holding current. So again, how do we trigger an SCR? If you apply a voltage that will make the the SCR go beyond the breakover voltage, the VBR. Once you trigger the VBR, the SCR will turn on. The same in the shock lead. But the purpose of the gate terminal for us to be able to switch the SCR faster than the shock lead. Because by applying the voltage at the gate, it can trigger the SCR faster for it to go on the turn on state. Then we have breakdown. We cannot use the SCR directly in an AC supply, because once the SCR receives a negative supply, it will break the SCR, just like in the shock lead diode. That's why most of the time we use diac as a triggering device for the SCR, because diac is a bidirectional or diode in AC. How do we turn off? We don't turn off SCR by just removing the gate, the voltage on the gate terminal. We have to make the current in the SCR below the holding current for it to turn off. Just like in shock lead, you have to gradually lower the input voltage for it to turn off. Okay, so this is the characteristic curve. We do not go beyond the reverse blocking because it will damage the SCR. So here, the IG refers to the voltage that you want to apply. At certain IG, it will trigger it faster. Okay, so we have a forward blocking. When you reach this one, it will be in the forward conducting. We don't have reverse conducting mode in the SCR. So we have two transistor model. So it's equivalent to this one. As you can see, it is just the same as the shock lead diode, but you produce a gate terminal here. So meaning, why do we need this? Because when we are going to use the everycircuit.com, we do not have a specific symbol for this one. So you have to know what is the transistor equivalent model of the thyristors. So we have thyristor turn-on methods. So we have temperature triggering, we have light triggering, we have forward voltage triggering, we have rate triggering, and the gate triggering. Voltage rate triggering. So thermal triggering, the width of the depletion layer of the SCR decreases with increased in junction temperature. Therefore, in SCR, when the anode to cathode voltage is very near to the breakdown voltage, the device is triggered by increasing the junction temperature. By increasing the junction temperature, the reverse bias junction collapse. Thus, the device starts to conduct. This type of turn-on may cause a thermal runaway and is usually avoided. The increase in temperature is within the specified value, otherwise it may burn the device. So there is also a thermal triggering, but again, thermal triggering, we are careful in using the thermal triggering because most of the components that we have are sensitive in temperature. That's why we avoid using a thermal triggering. For light triggered SCR, a special terminal is made on the side of the inner P layer instead of a gate terminal. When the light is allowed, when you strike this terminal, free charges are generated. When the intensity of light becomes more than the normal value, the thyristor starts to conduct. That is the LASCR. Energy is imparted by the light radiations, either neutrons or protons. Electron-hole pair are generated by increasing the number of charge carrier. This leads to instantaneous flow of current and thyristor triggering. Should have a high voltage derivative. As we go along the thyristors, most of the time, we need to break down the junction 2 for the thyristor to work. Forward voltage triggering, this is usual. The forward voltage triggering, the applied voltage across anode to cathode. So I don't need to discuss this further. Again, we have latching current and the holding current. The rate triggering, the voltage rate triggering. With forward voltage across the anode to cathode, the outer junction J1 and J3 are forward bias. This is J3. But J2 is reversed. J2 behaves like a capacitor due to the charges existing across the junction. If the rate of rise of forward voltage is high, charging current could be more, acting the gate current and triggering the thyristor. Therefore, when the rate of the change of voltage across a device becomes larger, the device may turn on even if the voltage across a device is very small. So that is the voltage rate triggering. So we have gate triggering. You know this already. I've discussed this. If you apply the voltage across the gate terminal, positive voltage, by this making the SCR trigger faster because you're adding more positive voltage to the supply current. So we have three types of gate triggering: the DC gate triggering, AC gate triggering, and we have pulse gate triggering. As the name implies, yun na yun. DC voltage, AC voltage, and the pulse voltage. Pulse triggering is the most popular. Pulse transformer is used for isolation. No need to apply continuous signal because we know that the SCR, once you trigger the SCR through the gate, it will turn on. No need to apply because you meet the holding current. You meet holding current plus you go beyond the current supply. That's why it is on. No need to continue supply signal because it is pulse. Sequence of high frequency is called the carrier frequency gating. In this method, the gate drive consists of a single pulse appearing periodically. A sequence of high frequency pulses. This is known as the frequency carrier gate. So we have firing angle. Firing angle A, it is the angle after which a thyristor fires off conducts. It is normally done by either analog, digital, or microprocessor controller circuits which sends the desired pulse of the thyristor gate drive circuit that will produce an actual gate drive pulse. Varying this angle changes the effective RMS value of the voltage and current and hence power. Thyristor protection for reliable and satisfactory operation. The specified rating of SCR should not exceed due to overload, voltage transients, and other abnormalities. Due to the reverse process in SCR during turn-off, the voltage overshoot occurs. In this short circuit, a large current flows through the SCR which may damage the device. Protection, DIDT protection, DVDT protection, overvoltage protection, overcurrent protection, and thermal protection. Current rate protection, voltage rate protection, snub circuit, overvoltage protection, cause of external overvoltage, protection against overvoltage, overvoltage prober protection circuit. Here is an example of circuit with SCR. As you can see, I have a load of motor, then I have an SCR and switch. I have a pulse generator for the gate terminal and the sinusoidal wave for the input terminal. When the switch is open, the input is a square wave. When you switch it on, as you can see, the output of the waveform of the load, which is the motor, became a spike or sawtooth-like, indicating that the motor is running then stopping. So this is an example of a generator using pulse as gate triggering and SCR. We can change the generator and convert it into LED. As you will see that it will become a blinker. Same output as the one in the motor. We look at the output waveform, it will be sawtooth. Okay, so this is the simulation.